Hello everyone. In this lecture, we will focus on a different technique for clustering called hierarchical clustering. Let's start. So as a recap, in the previous lecture, we discussed what do we mean by supervised learning and how it is different, unsupervised learning, and how it is different from supervised learning. We also discussed among many tasks available in the unsupervised learning domain, we focus on clustering and K-means clustering as a famous clustering algorithm. In today's lecture, we will be focusing on hierarchical clustering. There are two basic types of hierarchical clustering. So in this lecture, we will focus on agglomerative hierarchical clustering. There is an associated concept related with the hierarchical clustering called linkage. We will discuss that also and its types. And there is a very specific visual representation of hierarchical clustering called Dendrogram. So we will discuss this also in our lecture. As a reminder, let's discuss the definition of clustering once again. So clustering is the process of grouping the data points or objects based on the similarity so that the data points within the cluster or group are similar and they are dissimilar to the rest of the data points remaining in different clusters. K-means algorithm is one of the ways to do the same. We also discussed this example in the last lecture where we implemented K-means clustering on ready-made cloth grouping dataset. If you remember, depending upon the value of K, either we can have 3 clusters or 4 clusters. It is important to mention that in K-means clustering algorithm, K plays an important role and its value might affect the performance measures related to clustering. So as I told you, in hierarchical clustering, K is very significant. But then an obvious question is how we will decide the value of K beforehand actually in K-means clustering algorithm. And this can be seen as one of the limitations of K-means clustering algorithm. On the other hand, hierarchical clustering works in a different fashion. In general, hierarchical clustering is a method of clustering data points into a hierarchy of clusters. It starts with each data point as its own cluster and then merges the closest clusters until only one cluster remains. This process creates a tree-like structure that we call dendrogram. This dendrogram represents the hierarchical relationship between the clusters. There are two main types of hierarchical clustering called agglomerative clustering and divisive clustering. Agglomerative clustering is the most common approach. It begins with each data point as a separate cluster and then merges them into clusters at each step until all points belong to a single cluster. So this algorithm proceeds iteratively by merging clusters until a stopping criteria is met. Typically, the stopping criteria is based on a distance threshold or a specific number of clusters. On the other hand, divisive hierarchical clustering starts with all data points in one cluster and then recursively splits cluster into smaller groups. While conceptually simple, divisive hierarchical clustering is less commonly used in practice due to its computational complexity. That's why in today's lecture we will focus on agglomerative hierarchical clustering. So you can say that agglomerative hierarchical clustering is a bottom-up approach. It considers each point as separate and then form them into clusters like this. On the other hand, divisive hierarchical clustering is a top-down approach which starts all the points as one cluster and then divides them into smaller clusters. So let's try to understand agglomerative clustering, which is a part of hierarchical clustering, with this example. Let's say we have this data set with three variables, x1 and x2 and x3. In this specific example, we are using the color coding to represent the values. You can say that brown color might represent a very high value and dark like this, and dark blue might represent a very low value. So we have 4 data points with these values of 3 variables represented by the colors. So in agglomerative clustering, initially each data point is a separate cluster. Or we can say that at step number 1, we have 4 clusters in hand. Now as the next step, what we do is we check the similarity between each pair of data points and then we try to combine them. So we have to check whether 1 is more close to 2 or 3 or 4, or 2 is more close to 3 or 4, or 3 is more close to 4. So whatever pair seems to be the closest to one another, they will be combined and form cluster. By color coding, it can be observed that point number 1 and data point number 3, they seem to be very close to one another than any other pair, because for both of them the first value is very close in color shade, means they are very close in number also. The second point also, the second dimension x2 is also very similar, and the third one is also very similar in comparison to any other pair. Now since 1 and 3 they are closest than any other pair of points, we will form a cluster out of them. So after second step number 2, we got 3 clusters. 1 and 3 as one cluster, and 2 and 4 are separate clusters as of now. Now as the next step, we have to check which of the pair is more close to one another. So we have to check whether 1 is closer to 2, 1 is closer to 4, or 2 is closer to 4, or 4 is closer to 1. So whatever pair 1 2, 1 4 or 2 4 turn out to be closer to one another, we will combine them and form another cluster. Now one obvious point here is that it is easier to compare the closeness between the points, but how we will check how close a specific point is with the whole cluster? We will discuss this concept later on. But as of now, it turns out that 2 and 4 are more close to one another. That's why we combine them into one cluster, and now we have 2 clusters, cluster 1 and cluster 2. The combining of these 2 points has been shown here also. Here, as you can see, that this structure is shorter in length then the second structure, which represents that 1 and 3 were combined earlier, so that's why their length is shorter, and 2 and 4 were combined later, that's why their length is longer. This structure in hierarchical clustering is called dendrogram. As the last step, we will combine all the points together into one cluster, and we represent that like this. So first, this formation was done, these 2 points formed one cluster, then these 2 points form one cluster, and then these 2 clusters were combined to form this overall cluster. This is how hierarchical clustering or agglomerative clustering, to be specific, works. Now there are a few points to be discussed here regarding hierarchical clustering. First of all, let's discuss dendrogram. So when we see dendrogram, it represents two things: the degree of similarity between points. The shorter the length is, the more the degree of similarity there is between those clusters, and it also tells the order of formation. Since once again the length is shorter here, it means this grouping was done earlier than the second grouping, because here the length is longer. So shorter length in dendrogram represents two things: that those clusters are more similar, that's why they were joined together earlier. Another important consideration is how you will decide the similarity between points. Like in k-means clustering, here also we rely on distance measures, primarily on Euclidean distance. There are other distance measures also, like Manhattan distance. Depending upon the choice of distance, the formation of the hierarchy of clusters might differ in hierarchical clustering. Now comes another important concept related to hierarchical clustering, that is how we will compare a given point with the cluster. That is, if I have this cluster with multiple points here and one more cluster with multiple points here, and I want to check whether this new point belongs to the first cluster or the second cluster, then how we will do that? There are a few choices. These three choices are more common. Either we can take a centroid approach, in which we calculate the centroid or the average point here of both the clusters, and we will calculate the distance with each of these clusters, and we will assign this new point to the cluster depending upon to which centroid it is more close. Or we can also use the single linkage approach or complete linkage approach. Let's discuss them further. So as we want to see that to which specific cluster this black point should belong to, either this cluster or that cluster, there are three choices. Primarily, there are other choices as well. First is the centroid approach. We calculate the average or centroid of each cluster, and then we calculate the distance of the given point with these two centroids in this specific case. We can also use the single linkage approach, where we calculate the distance of the given point with the closest point of each cluster. So as you can see here, we are calculating the distance of this point with the closest point here and the closest point there, and to whichever it is closest, we will assign this new point to that cluster, or we can also use the complete linkage approach where we calculate the distance of the given point with the farthest point of each cluster. So in this case, we are considering this point, and for this cluster, we are considering the farthest point of this cluster. And once again, depending upon the distance, we will assign it either to cluster 1 or cluster 2. So we can use any of these approaches. Remember, depending upon the choice of the linkage, the formation of clusters might vary. Now let's see one example to understand the agglomerative clustering in a better. Let's say I have these 6 data points and my data has only 2 variables, x1 and x2. So to apply the clustering algorithm, hierarchical clustering, in this case agglomerative clustering, we will calculate a distance matrix. But as the first step, we consider each point as a separate data point, separate cluster. So 1 is a separate cluster, 2 is a separate cluster, and so on. Then we calculate the distance matrix for each point with every other point. So first row here represents what is the distance of 1 with point with cluster 2, with cluster 3, with cluster 4, 5, 6, and so on. There are other points as well. Initially, points and cluster represent the same thing because each point is considered a separate cluster. It is also noteworthy that the row values are same as the column values. So once we calculate the row, the same value goes in the column also, the first column. Same is true for the second row. So second row here represents the distance of 2 with rest of the points here, and this is true for the column as well. Let's see how this distance is calculated. We have used the Euclidean distance formula here. For example, let's see what is the distance between cluster 5 and cluster 4. What is the distance between these 2 points? So we know that cluster 5 here is 4, 4 and cluster 4 is 3, 4. So the distance is 4 minus 3 squared, 4 minus 3 squared plus 4 minus 4 squared, 4 minus 4 squared, which means 1 squared, which means 1. So that's why the distance between 4 to 5 is 1. In this way, we have calculated this distance matrix. Now the next step is we will see which of the value here is the smallest distance value. If you observe that in this matrix, apart from the diagonal values, obviously, if we leave them because they represent the same point, distance from the same point, you will see that 0.5 is the smallest value and it represents the distance between cluster 4 and cluster 6, which can also be observed in column also, 0.5, which means the distance of cluster 6 with cluster 4. Now what this 0.5 represents? It represents that 4 and 6 are closest, this pair is closest to one another than any other pair. So what we will do is, we will combine 4 and 6 together in one cluster, which will affect the distance matrix. So as we have observed here that 0.5 is the closest value, we decide that 4 and 6 should be merged and we update the distance matrix. This is how we update that. So the rest of the values will remain same, but we have to identify what would be the distance of cluster 1, which is a data point right now, an individual data point, from 4 and 6. So how far 1 is now from the cluster 4 and 6, not the data point 4 and 6, but its cluster 4 and 6. For that, in this specific example, we are using the single linkage. That is, we will calculate the distance of 1 with the 4-6 cluster to which it is the nearest. So 1 out of this 4-6 cluster, 1 is 3.61 units away from 4 and 3.20 units away from 6. So we will say that the cluster 1 is 3.2 unit away from the cluster 4 and 6. That's why the value here is 3.2. Remember, if we will be using the complete linkage approach, then we should select the value 3.61 because complete linkage considers the farthest point from the given data point. The same goes for other clusters as well. Let's do one more example. Let's say I want to check how far 3 is from the cluster 4 and the cluster 6. If you observe, then cluster 3 is closer to 4 and this distance is less than distance 6. So we will say that the distance between that cluster 3 and the cluster 4, 6 put together is 2.5 because we are considering once again the single linkage property. And in this way, we update the values. Remember, the rest of the values will not change because we are not combining these clusters together. So after first step, we now have 5 clusters, 1 as a separate cluster, 2 and 3 and 5 as separate clusters, so 4 clusters here, and 4, 6 as a combined cluster. Now once again in the next step, from the updated distance matrix where 4 and 6 has already been combined, we will see that which of the value is the minimum apart from the diagonal values. So it turns out that 0.71 is the minimum, which represents that after 4 and 6, 1 and 2 are closest pair than any other possible pair. That's why we will combine 1 and 2 as well, and we will update the matrix once again. For example, we want to know what should be the distance of, once we have combined 1 and 2, what should be the distance between cluster 3 and this newly created cluster of 1 and 2. We will see what is the distance of 3 with 0.1 and 0.2, cluster 1 and cluster 2. Since we are using the single linkage approach, we will observe that 4.95 is smallest than 5.66. So we will say that cluster 3 is 4.95 unit away from this newly created cluster 1, 2. So this is our updated distance matrix after step 2. And now the number of clusters remain 4. So this is one cluster now. This is cluster number 2. This is the third cluster and this is the fourth cluster. We will repeat the process once again. We will once again identify what is the minimum among the values of the decision matrix. 4, 6, this cluster and the cluster 5, they are closest to one another than any other pair of clusters. So we will combine them once again. We will update the matrix, and now the number of clusters remain 3. This is our updated matrix. We will repeat the process once again, the same process. There are 2 clusters left now. And lastly, we will combine all the points together to form one whole giant cluster. So this is how hierarchical clustering works. Agglomerative clustering, to be specific, which considers each data point as a separate cluster. We start from that point and it ends when all the points are combined together to form one cluster. So the beauty of this algorithm is that if you want to consider 6 clusters, then you have each data point as a separate cluster. If you want to consider 3 clusters, then you can use this organization or grouping. If you want to consider 2 clusters, then you can consider this grouping, and so on. So it does not force you to predefine the value of k, that is the number of clusters. And this is the corresponding dendrogram here. You can see that this line is shortest than any other line, which represents that 4 and 6 were combined as the first choice, then rest of the combinations, then came 1, 2, then came the combining of 4 and 6 cluster together with the 5th cluster, and so on. And this is how this dendrogram is created. So in summary, we discussed hierarchical clustering, and the benefit is that it does not require a predefined value of number of clusters, and agglomerative clustering is one of its type which can be implemented using Python very easily, as we will see very soon. Now let's see the implementation of hierarchical clustering. I have already mounted my drive. Let me import the necessary libraries here. As you can see, we are importing the agglomerative clustering function here, and we are also importing dendrogram and linkage functionality in order to view the clustering. Let me upload the same dataset as we use in the k-means clustering. As you can see that the size of the dataset is same. It has 150 rows with 2 columns. Now using the function agglomerative clustering, we can create the hierarchical structure, and there are a few things that you can mention here. You can mention the number of clusters. You can mention the similarity measure, which is Euclidean distance. You can also mention what kind of linkage we want. In this case, we are using the single linkage. And we can also mention the distance threshold where the algorithm should stop. If we do not mention any number of clusters, then it will consider every point as a separate cluster. So when we fit the data, the algorithm is applied, and let's plot the data. As you can see here every data point is considered as a separate cluster. If we want to, we can change the number of clusters, let's say 3, and in that case the threshold should be set to none. Now if we do that and run the model once again, you can see that now 3 clusters have been created. The blue cluster is here. You can see only one point in the yellow cluster. and then you see this black cluster as well. Let's try to change the value of k, that is 2, and this time you will see only 2 clusters. One is represented in yellow and the other is represented in black. So this implementation is very straightforward, and with the help of inbuilt libraries, we can easily implement hierarchical clustering technique. So this is all about today's lecture. Thank you.